Section 5.4 is all about dividing polynomials. Our objective is that we can use both long division as well as synthetic division to divide polynomials. The main idea that you want to get from this lesson video is that dividing one polynomial by another will help us factor polynomials, and that's what we've been doing the past several sections. When we try to factor a polynomial, we are actually trying to find a divisor of the polynomial that gives us a quotient, which is the other factor, and a remainder of 0. So say, for instance, we are trying to factor the expression x squared plus x. Well, we know by now that we always want to look for a GCF, and in this case there's a GCF of x, so we factor out x. The way that we figure out what's inside the parentheses is we're essentially dividing the original polynomial divided by x, which is the GCF. That's how we get x plus 1 inside the parentheses. I would like to show you how to use polynomial long division in order to obtain the same result. So say we have x squared plus x and we're dividing by x because we know that's a factor. We think to ourselves, how many times do we have to multiply x to get x squared? Well, we just need to multiply x by itself to get x squared. So x times x is x squared. And we are subtracting. So then that cancels out the x squareds. So we just drop down x. Well, what do we have to multiply x by to get itself? And that is 1. So plus 1. So when you multiply x and 1, you just get x, and you subtract and you get 0. So this expression, x plus 1, is the other factor, and we just got a remainder of 0. This is how we're going to be using the polynomial long division to assist us in the factoring process. If we're able to use the GCF process to factor the polynomial, then we would do that instead, because obviously that's simpler. But today we're going to be dealing with polynomials where we can't necessarily use a GCF or the other methods that we've used before. Let's take a look at numerical long division from elementary school, actually, and polynomial long division, which is what we're learning today. They have similarities, so that's why we're talking about numerical long division first. So say, for instance, we're dividing 672 by 21. What we want to do is think to ourselves, how many times do we multiply 21 in order to get a number that's below 67? Well, we could fit 3 21s into 67, and that would be 21 times 3 is 63. When we subtract, we get a remainder of 4, and you drop down the 2. How many times can you fit 21 into 42? You can fit 21 2 times exactly, so we multiply 21 times 2 and you get 42, and when you subtract you get 0, so the remainder is 0. So that means when you multiply 21 and 32 you get 672. Polynomial long division is very similar. The only difference is we have variables involved. And you can notice that these are the same numbers as in the numerical long division we just talked about. So in this problem, we're trying to figure out, is 2x plus 1 a factor of the polynomial 6x squared plus 7x plus 2? The way that we figure out it's a factor or not is if we get a remainder of 0. If we get a remainder of 0, then that means it is a factor of the given polynomial. So when we divide 2x plus 1 into the polynomial that we're given, we need to think to ourselves, what number do we have to multiply 2x by to get 6x squared? And the answer to that question is 3x. So when you multiply 2x times 3x, you get 6x squared, and when you multiply 3x times 1, you get 3x. From there, you want to subtract, so we are subtracting the given from the original. So the 6x squareds cancel and you get 4x left, and you drop down the 2. Now you think to yourself, what do you have to multiply 2x by to get 4x? And the answer to that is 2. So when you multiply 2 times 2x, you get 4x. And when you multiply 2 times 1, you get 2. And when you subtract that, you just get a remainder of 0. So that means 2x plus 1 is a factor of the given polynomial. And when you multiply 2x plus 1 times 3x plus 2, you get that original polynomial. And you can always FOIL to check to make sure it worked for you. In example 1, we're going to be using polynomial long division to divide 4x squared plus 23x minus 16 by the expression x plus 5. What is the quotient and the remainder? Setting up our long division, I have the quadratic underneath the division bar and x plus 5 in front. So the dividend is the number that we're dividing into, and the divisor is the number that we're dividing by. So the first thing we want to do is think to ourselves, how many times does x, which is the number in front, fit into 4x squared? So divide 4x squared by x, and we get 4x. So that is the first number that we want to work with. And the way that you figure out where to place the first term in the quotient Taking a look at the bottom right corner, I have this written down. The term of the quotient is placed over the term in the dividend of the same degree. So we have 4x that has a degree of 1, the indivisible exponent of 1. So that means we're going to place the 4x right above the 23x because it has the same degree. So now we want to multiply 4x times x plus 5, which is the divisor. So we are just distributing that, and we get 4x squared plus 20x. So that is what goes below. And we will be subtracting that, and I always put parentheses around my expression so I know that I'm sharing the minus sign to both terms. So when subtracting, I get 4x squared canceled, and then I get 3x remaining, and I drop down the minus 16. Taking the first term, the 3x, I think to myself, what is 3x divided by x, which is the number in front, and I get 3, so that means I'm multiplying by 3. So now I want to multiply 3 times x plus 5. And when distributing the 3, I get 3x plus 15. So that's what I want to write right below. When subtracting, the 3x cancels, and I get negative 16 minus 15, which is negative 31. So that means my quotient is 4x plus 3, and the remainder is negative 31. So you may be thinking to yourself, how do you know when you are finished dividing the polynomial? Well, you know you're done when the degree of the remainder, in this case the remainder is negative 31, so degree is 0 since there's no variable at all. If the degree of the remainder is less than the divisor, well, the divisor had a degree of 1 because an invisible exponent of 1, and the remainder has a degree of 0, so that means the degree of the remainder is less than the divisor, so that means we are done. I'd like to briefly talk about how to check your answer. The way that you check your answer is you show that the divisor times the quotient plus the remainder is equal to the dividend. So in this case, our divisor was x plus 5. Remember, that's what we were dividing by. The quotient is what we got for our answer just a moment ago. The remainder is what we have left over, which in this case was negative 31. We need to show that when you do those operations, you get the dividend, which was the original expression that we were dividing. So let's use FOIL real quick. 4x squared plus 3x plus 20x plus 15 minus 31. When you combine like terms, you get 4x squared plus 23x minus 16, and that is the dividend that we started with. So that is the checking process. This key concept box below generalizes the ideas we have been learning. It's all about the division algorithm for polynomials. When we divide a polynomial p of x by a divisor d of x, we get a quotient q of x. So the way that we check our answer, just like we talked about above, we take the divisor, we multiply by the quotient, so the number in front multiplied by our answer, and then add the remainder, and we get the polynomial that we started with. If we get a remainder of 0, then our polynomial can be written as the product of the divisor and the quotient. And that means the divisor and the quotient are factors of the original polynomial. The way that we're going to be using long division, and the way that we have been so far, is we make sure that the polynomial and the divisor are written in standard form, which means biggest exponent to smallest. If there are certain variables missing, like degrees, such as x squared, if there's no x squared at all, you'll still have a 0x squared in that spot. The process stops when the degree of the remainder is less than the degree of the divisor, which is what we talked about earlier. These ideas will obviously make more sense when we do an example together. In example 2, part A, we're asked if x squared plus 1 is a factor of the polynomial 3x to the 4th minus 4x to the 3rd plus 12x squared plus 5. We need to figure out if we have a remainder of 0. If that's the case, then x squared plus 1 is a factor. One more thing before we get started, make sure you put 0x in for the missing spaces because both the dividend and the divisor were missing an x term and we have to account for that. So we have zeros in those spots. Okay, so now we want to think to ourselves, what do we have to multiply x squared by in the divisor to get the first term of the dividend, which is 3x to the 4th? We need to multiply x squared by 3x squared to get 3x to the 4th. So remember, we're lining up the x squareds. So then now we need to multiply. So when we multiply 3x squared by each of the terms inside the parentheses, we get 3x to the 4th plus 0x to the 3rd plus 3x squared. And that's what goes below right here. And now we need to subtract each of those terms, so we have the 3x to the fourths canceled. We still get a negative 4x to the third, and we get a 9x squared here. And you want to drop down the next term, which is just 0x. Now we need to figure out what do we have to multiply x squared by to get negative 4x to the third. We need to multiply x squared by negative 4x. That will give us negative 4x to the third. So now we're going to distribute negative 4x to each of the terms of the divisor. So we get negative 4x to the third minus or plus 0x squared minus 4x. So that's what goes below. And remember, we are subtracting each time. So when you're subtracting, you're changing the signs of everything inside the parentheses. So the 4x to the third, they cancel, and we get 9x squared plus 4x, and you need to drop down the last term, which is 5. Now, what do we have to multiply x squared by to get 9x squared? And that is 9. So we're going to multiply each term of the divisor by 9. So we get 9x squared plus 0x plus 9, and that's what we write below. When subtracting, the 9x squareds cancel. We get 4x minus 4. We don't need to go any further because the degree of the remainder, which in this case is degree 1, because the biggest exponent is a 1, is less than the degree of the divisor. The degree of the divisor was 2 because there's an x squared in the beginning. So that means we are done. So because our remainder is 4x minus 4 instead of 0, the expression x squared plus 1 is not a factor of the original polynomial. In part B, we need to figure out if x minus 2 is a factor of the given polynomial x to the fifth minus 32. If it is a factor, we need to write the polynomial as the product of the two factors. Remember, in order to get our answers, we always set our factors equal to 0. So I'd set x minus 2 equal to 0. I did my one step by adding 2, and I get x equals 2. So what we want to do now is plug in positive 2 in for the given polynomial x to the fifth minus 32. If we get a result of 0, then that means x minus 2 is a factor. When plugging in 2, I get a result of 0. So since p of 2 is equal to 0, x minus 2 is a factor of the given polynomial. Since x minus 2 is a factor, that means we can divide by that factor in order to get the other factor of the polynomial. So take a moment and set up your division just like I did, and notice that we do have zeros for the coefficients of x to the fourth, x to the third, x to the second, and x, and that's because those terms were not given in the polynomial, so there's zeros in front. Now pause the video and try to work through the polynomial long division by yourself, and I will pause it as well and work through it, and then you can check in a moment to make sure you understand. When dividing the given polynomial by x minus 2, I get a quotient of x to the fourth plus 2x to the third plus 4x squared plus 8x plus 16. And you notice at the bottom that the remainder is 0. So that means we are done here. So the polynomial in factored form would be shown right here in the bottom left-hand corner. So feel free to pause here to write down this work and take note of that I do have the side work on the side. If you don't understand this fully yet, don't worry, we will definitely be going in depth together in class tomorrow. Now we're going to be discussing the other process that helps us divide polynomials, and that's called synthetic division. It simplifies the long division process by dividing by a linear expression x minus a. In order to use synthetic division, we're going to write the coefficients, including zeros, of the polynomial in standard form. We're not going to be writing down the variables and the exponents until the very end. For the divisor, we're going to reverse the sign, which means we're using the a value. This is going to allow us to add instead of subtract throughout the whole process. Example 3 is going to give us the opportunity to learn how to do synthetic division. So we're going to be dividing the polynomial x to the third minus 14x squared plus 51x minus 54 by the factor x plus 2. We need to figure out the quotient and the remainder. So the first thing we want to do is reverse the sign of the given factor. So we were given x plus 2, but to write this in the linear expression form, x minus a, we're going to have x minus a negative 2. So the a value in this case is negative 2. We always put our synthetic divisor in the top left-hand corner. Now we're going to write the coefficients of the polynomial. Remember, the coefficients are the numbers in front of the variables. So we have 1, negative 14, 51, and negative 54. In this case, we did not have to put any zeros because there were no terms missing in between, but sometimes we will have to do that. Next, we want to bring down the first coefficient. So in this case, the 1 drops. Now we're going to multiply the coefficient 1 by the divisor negative 2. When you multiply those two numbers, you get negative 2. So write that in this blank space here. And then we're going to add to get the next coefficient. So we get negative 16. So we're going to be doing a multiplying and adding pattern until we get to the last coefficient. So now we're going to multiply negative 2 and negative 16. That gives us positive 32. And then add 51 and 32. And that gives us 83. Now we're going to multiply negative 2 and 83. That gives us negative 166. And we're going to add negative 54 and negative 166. And we get negative 220. So starting on the right-hand side, that last number is the remainder after dividing. So negative 220 is the remainder. The next term, the 83, is the constant, which has no variable attached to it. The negative 16 has an x attached to it, and the 1 has an x squared attached to it. So writing that in standard form, we get the polynomial x squared minus 16x plus 83. That's our quotient, and our remainder is negative 220. So you can see that that process was a lot quicker. You just need to remember what numbers to multiply by and what numbers to add by. And we'll continue this process in example 4 and 5. In example 4, we are told that the polynomial x cubed plus 7x squared minus 38x minus 240 expresses the volume in cubic inches of the shadow box shown. First thing we need to do is figure out the dimensions of the box. And the hint that we are given is the length is greater than the height, or the depth. The picture at right gives us the width of the box. Remember, for a rectangular prism, the formula for volume is length times width times height. Remember, for synthetic division, we need to write the factor as x minus a number. So because we're given x plus 5 as the original width, I can write that as x minus a negative 5. So that means the synthetic divisor that we're about to use is negative 5. So let's put that in the top left-hand corner. Now let's write the coefficients of each of the terms. So we have 1, 7, negative 38, and negative 240. The first step is to bring down the first coefficient, so we have 1. So now let's multiply the divisor by the coefficient. So negative 5 times 1 is negative 5. Now add 7 and negative 5, and we get 2. Multiply negative 5 and 2, we get negative 10. Add negative 38 and negative 10, we get negative 48. Multiply negative 5 and negative 48. That gives us positive 240. Add negative 240 and positive 240, and we get 0. So we have a remainder of 0. So I always write r below the last term, and then I write constant, x, and x squared. So those are the coefficients of each. So that means our factored form after dividing is x squared plus 2x minus 48. So that is our quotient. And now, look, it's a quadratic, and we can't use the x method, so we're about to do that. The numbers that work for the x are 8 and negative 6. So to write that in factored form, we can write x plus 8x minus 6. So that means the original polynomial can be written in this form. The quantity x plus 5 times the quantity x plus 8 times the quantity x minus 6. Because it told me that the length is greater than the height, I know that the length has to be x plus 8 because that is bigger than x minus 6. And we were told from the beginning that the width is x plus 5. So that means our length is x plus 8 inches, our width is x plus 5 inches, and our height slash depth is x minus 6 inches. So those are the dimensions of the box. In part B, we're told that the width of the box is 15 inches, so we need to determine what the other two dimensions are. Well, if the width is equal to the expression x plus 5, and the width is equal to 15, we can set those two equal to each other. So 15 equals x plus 5. Doing a one step, we subtract 5 from both sides, so we find out that x is equal to 10. Now that we know x equals 10, we can easily find what the length and the height are. The length would be x plus 8. Substituting in 10, we get 10 plus 8. So that means the length must be 18 inches. And to find the height slash depth, we just need to take x and subtract 6. So 10 minus 6 is 4 inches. So that gives us our other two dimensions for this problem. The remainder theorem is the last topic that we're going to discuss in this lesson video. And the remainder theorem gives us a quick way to find the remainder of a polynomial long division problem. So the remainder theorem says, if you divide a polynomial p of x of degree n is greater than or equal to 1, which means it's a linear degree or above, by the factor x minus a, then the remainder of that division is p of a. So here's an example to make it make more sense. What is p of 4 for the polynomial 4x squared minus 5x minus 20? The way that we can easily figure this out, in addition to synthetic division, is we can just substitute in 4 to figure out what we get. That will be our remainder. When substituting in 4 for the given polynomial, I get p of 4 is equal to 24. When we evaluate the polynomial at x equals 4, the result, which is p of 4 equals 24, is the same as the remainder when the polynomial is divided by x minus 4. In example 5, we're given the polynomial p of x equals x to the 5th minus 2x to the 3rd minus x squared plus 2, and we need to figure out what the value of p of 3 is. Without substituting, we can actually use synthetic division to find p of 3, which is the remainder. So by the remainder theorem, p of 3 is the remainder when we divide p of x by x minus 3. The synthetic divisor is positive 3, so we're going to write that in the top left-hand corner, and then remember you write all of the coefficients. And hopefully you noticed when I was reading the polynomial out loud that x to the 4th and x were both skipped. So in those places we put a 0 for the coefficient. So we have 1, 0, negative 2, negative 1, 0, and 2. You always bring down the first coefficient so the 1 drops. We're going to multiply 3 and 1, and we get 3. Add 0 and 3, we get 3. 3 times 3 is 9. Negative 2 plus 9 is 7. 3 times 7 is 21. Negative 1 plus 21 is 20. 3 times 20 is 60. 0 plus 60 is 60. 3 times 60 is 180. And 2 plus 180 is 182. So that means my remainder is 182. To show you that we get the same result, I'm substituting in 3 for the original polynomial, and when I do all those operations, I get 182. So that confirms that we did synthetic division correctly. For the section 5.4 lesson check, I'd like to do numbers 2 and 4. For number 2, use long division. For number 4, use synthetic division. And if you need extra practice, feel free to do the odd numbers and check your answers with the back of the book for the odd numbers. If you are not 100% confident with this lesson, do not worry. We'll definitely go in depth together when we go over this together tomorrow.